give a very warm welcome to Mohammad Ghassemi, the co-founder of Ghamut Corporation. Hi.
Thank you. Good afternoon. Hope you're all doing well. I've really enjoyed the talk so far, and it's really a pleasure to be up here on the stage with you and to speak a little bit about some of the work that I've done at the intersection of artificial intelligence, health, and behavioral science. So very quickly about me, I recently completed my PhD at the Massachusetts Institute of Technology. I was there for about 6 years. I got a PhD, and I wrote about 24 papers. And starting next year, I'll be a faculty in Michigan in the Department of Computer Science. Between now and when I begin my faculty appointment, I'm working on a startup company, the Ghamut Corporation. And today I'll be telling you about a couple of the research projects that the Ghamut Corporation is involved in, and how I think they're playing an important part in helping advance some things in the field. So anytime I give a talk that's about artificial intelligence or data science, I'd like to remind people that it's called data science because it's data first and science second. And I think it's also interesting to think about some elements of the history of data when you're talking about data science. Back in 1967, if you wanted to have a megabyte of storage, it would have cost you $1 million, and it would have been this giant 1-ton device that you would have to sit probably in a cooled room if you wanted to have access to that data. So very understandably, the way that algorithms were designed, like let's say an algorithm to figure out whether an image is an apple, wouldn't use just the pixels of the image when it wanted to make a prediction. Instead, you would featureize some things that were essential to the apple, like the old Socratic or Platonic way of doing things. What is an apple? Well, an apple is a round object. An apple comes in certain colors. An apple may have a stem, and an apple may have a leaf. And if I store just those information, let's say as binary things, I can detect whether an object is an apple or not for a very small amount of space. So I don't have to blow millions of dollars on the disks. Well, obviously, data is no longer that expensive. It's now a mere 2 cents a megabyte, at least last time I checked. And that basically made it so cheap to keep data that none of you in the audience probably even delete your photos anymore, or emails. At least I know I don't, right? In fact, it costs more in terms of the value of your time to go through the data and to choose what to delete than it does to just kind of store it. So the analogy there is that we have millions and millions of images of these apples. They may not be as high quality, but we can use something about something about the information across those images to teach the algorithms to do the detection instead. Okay. So remember, data science starts with data, and then it moves to science. So when we want to talk about things in the context of healthcare, as we've heard many other times here today, good data is essential. But in order for us to even assess whether the data is good, the data has to be available for people to look at, to analyze, to compare with others. And so one of the things that we've made an effort to do in my laboratory is to help with this idea of liberating access to data sets. One of those data sets is the MIMIC3 database, which is the information of 50,000 patients at the Beth Israel Deaconess Medical Center in Boston, Massachusetts. And anybody here in the audience who's interested in seeing that entire complete electronic medical record system with the patient notes, radiologists' reports, patient vitals, information on the care providers, all that stuff is available in Mimic, totally free. You can go on Google today, pull up the page, and you can have access to it. And so one of the things we've done in our laboratory environment is to ourselves use access to that information so that we can come up with algorithms that help improve care at the bedside. One algorithm that we developed recently, for example, was a medication dosing approach, where we looked at, across those 50,000 patients and the providers that were dosing sensitive medications, if we could learn ways to automate that so that we could provide dosing recommendations at the bedside. Now, of course, the natural next step, once you have access to large amounts of data, and you have abilities of members of the scientific and industrial community to collaborate around checking those and double-checking them to make sure that the quality is good, is trying to take some of that work and release the algorithms or push them out into the public domain. And one of the things that, example of that in our work recently that was mentioned in MIT News just about a week ago was an algorithm that used interviews from depressed people in a clinical environment, and but only uses the audio on your phone. So it could very easily, we hope, be generalized outside of just the clinical context. OK, so again, data science is about data and then science. And what I'd like to do today, we will talk about the coach. I'd like to take you through a journey of basically a data collection process, a scientific process in the clinic, and then a scientific process outside the clinic that utilizes these interesting data sets to solve pertinent problems in health. So let's start with the data. Well, let's think back first to 1967, when the cost of data was enormous to keep that 1 megabyte. If you went up to your boss and said, hey, I've got this great idea. We want to collect a big data set, and we're going to store it all on disk, they'd probably laugh at you and say, why don't you store it on a very cheap alternative? It's called paper. And that was a practical thing to do. Well, if you want to study things in health nowadays, almost everyone has an electronic medical record. And as we saw with Mimic, some of us are making efforts to release that to the scientific community. But the problem is a lot of the information is still actually locked away on these paper records. And when you're talking about rare ailments or diseases and you don't have large numbers of samples, the information on those records could be very important for what it is that you want to accomplish or build an algorithm to accomplish. Inside of those records, though, it can be a little bit of a mess. The data is very heterogeneous, different background colors, different cell sizes. Sometimes your handwriting spills outside of the cell, different ink colors, cross-throughs, all this heterogeneity in order to do the automation task, which makes it tricky. So the first thing I'd like to do is tell you about a system that we came up with to help pull some of this information out of the spreadsheets. We basically came up with an algorithm that first and foremost takes a very simple spreadsheet, something like this, and runs a series of image processing tasks on top of it to identify the grid lines and ultimately separate the cells into individual units. So here's an example with an actual clinical flow sheet from the Massachusetts General Hospital. There's a couple things I want to point out. The first one is that the page is bent, and the second thing is there's difference in lighting. So, real-world data in that sense. But you can see that the grid lines are identified they're identified well by the software. If you're interested in using this software for your own purposes, by the way, it's available on my GitHub page for free. So great. You have an image, something like this, and you've turned it into something like this. Well, now what you want to do is you want to extract digits. Why? Because the oldest, most classical machine learning problem is what? Is digit detection. So this should be a piece of cake, right? So great, you have your machine learning algorithm, whether it's a deep net, an SVM, a logistic regression, whatever your favorite is, and you've trained it on MNIST and some other data so that you can classify the contents of those spreadsheets and get it into digital form to use for your machine learning for rare diseases. And the tricky thing is this, that the machine learning agent is inevitably going to do well on some of the digits. Maybe it's 99% confident that that's a 1, and then it's not going to do so well on others. Maybe it's 30% confident that's a 2 because my handwriting is not so good. And there's inevitably going to be a set of the data, a subset of the data that you put into this that it doesn't do so well on. So what do you do for that? What do you do when the machine is not confident? Well, you do the reasonable thing. You give it to a human. Why wouldn't you, right? You wouldn't want the machine to be classifying something it's not confident about. And so long as it can indicate its confidence, then you'll be more comfortable when it does provide you with answers. So you can take things like the 24 there, and you can use services like Amazon's Mechanical Turk and crowdsource and get the answer to that for pennies a task. It's actually quite cheap. It also has the advantage that it preserves health information, or private health information. And you can feed that information now back to the AI agent so that it continuously improves. It's not a static one-off thing, but it's an algorithm that can improve over time. OK, great. So you might be wondering at this stage, well, hey, Mohammad, what inspired you to go and write a spreadsheet transcription algorithm? That sounds crazy. Well, it was because actually for this little thing called my PhD, I needed access to some of the data inside of those records. And so I built that to do this project that I'm going to tell you about here. I was interested in cardiac arrest. and particularly patients who are in coma after cardiac arrest, which is actually a pretty rare condition to study. So cardiac arrest is unfortunately on the more common side. It affects 320,000 people a year in the US annually. And about a third of them will end up being found and successfully resuscitated. People will do CPR, they might get a shock, and their heart will start up again. But between the time when they're down and when the resuscitation occurs, there's going to be anoxia-induced damage. Their brain, which is an oxygen-hungry organ, will want oxygen that's not there, and damage occurs. And so some very small fraction of them, about 5,000 out of the original set, are the ones who are going to regain what's called normal neurological status. So if you arrive in the ICU with this condition, you're going to be placed somewhere on this 5-point scale. Really, for our purposes, it's good or it's bad. Can you resume independent activity? That's blue. Or can you not resume independent activity? That's red. And the current prognostication guidelines have, which although they do well, they can be error-prone in as high as 20% of cases according to the scientific literature. So great. Well, we had fortunately taken that software I showed you earlier, and we had extracted a bunch of the important clinical information from those old documents on several patients at the Massachusetts General Hospital, 3 hospitals here in Europe, and another couple in and around the Boston area. And we took those in addition to recordings from the person's scalp. These are electroencephalograms. And we used some feature engineering to identify the sets of things that we thought might be pertinent to predicting whether these people would wake up. Basically 3 things. The first one was complexity. Hopefully you can see from those 2 waveforms that the one on top is more squiggly than the one at the bottom, so it's more complex. That's a good sign if you're going to wake up from a coma. The second one was the category. So clinicians have certain ideas about what kinds of categories that exist inside of brain recordings are good or bad signs. So we intentionally coded for some of those. These are things like burst suppression, which I hope is obvious from the waveforms and the movement that you see up there. And the third one is connectivity. The brain has a quality that's a little bit like a radio station in a community. If there's lots of differences or lots of different channels, that's a great radio community. If there's only one channel, it's not so good. So what you want to see is that as a function of which electrode you're looking at on the scalp, you're seeing differences in activity. That's also a good sign. So the point was not just to use, we also did this with deep learning, but the point was, if you want to take this and have the machine learning give you suggestions on the basis of what a clinician would actually trust, it takes careful collaboration with the clinicians around the knowledge base that they start with, so that you can create tools like this, which is actually on schedule to be deployed at the Massachusetts General Hospital, hopefully in the next couple weeks. Okay, so all of that was a long way to go to get us to this AI social coach. Well, where does it come from? That was the original thing of my talk. Well, that's because when I got towards the end of my PhD, I ended up realizing something, after working on coma for so long. It's great to be able to prognosticate when a person is going to wake up from a coma or not. But it doesn't tell you anything about how they got there, why they got there. Could you have maybe stopped them from getting there? You have an overglorified crystal ball in some sense with the AI that I described earlier, but it doesn't change the behavior that led the person to that unfortunate outcome in the first place. So the purpose of the Ghamut Corporation is to see right now, can we do that? Can we try to affect things about people's behavior so that we can lead to better health and behavioral outcomes before they end up in a critical ecosystem? Okay, and the first one that I chose to work on was one that's near and dear to my heart. Is social awkwardness. And that's because you see the gentleman sitting on the far right with his arms crossed. I oftentimes, when I'm at Thanksgiving dinners in the United States, feel like that guy. So I feel a little bit socially awkward. And it's usually not clear, unfortunately, if you're on the socially awkward side of the spectrum, exactly how you engage in conversations. Because you're socially awkward, you interact less, which means you get less practice, and it's sort of this self-fulfilling loop. So I thought, okay, well, here's a problem that's interesting and near and dear to my heart, so why don't I think about it? Why don't I take a shot at this? And so the way we did that was we collected a very simple data set, actually, at MIT. We just asked students that we knew around campus. We invited them to tell us stories. Very little structure on the stories, just as long as you want. The only constraint is you have to tell us at the end of the story whether you thought it was a happy one or a sad one. We collected 10 participants, 6 girls, 4 boys on campus, and then we rigged them up with a wearable device from Samsung, and we just put the audio on their phone on. And we thought, OK, let's collect that and some transcriptions of what they said and use that for machine learning so that we can ultimately figure out, is this conversation going well or is it not going well when we're speaking to them? OK, the problem is, though, that when you talk about 10 subjects, you're not talking about big data in the classical sense. We heard from Professor Gary Marcus that there's a lot of interesting problems where we don't have big data sets available, and we thought this was one of those examples. So we had to be very careful in what exactly we look at so that we don't overfit the models. What are the subset of things that we think are most important? Fortunately, the machine learning community has automated solutions to this through things like forward selection, where algorithms can determine on their own what are the sets of features that are most important to keep and retain from a larger set of features so that you can do a decent job generalizing your classification. Now, instead of me telling you, the exact topology of the neural network that was used, I thought it would just be more fun to show you the algorithm in action, and then you can read the papers if you'd like those technical details. So here it is. You can see on the top is the text, and it's colored according to whether it was happy or sad. So red is happier, blue is more sad. So as you see the dot moving, you'll see that the algorithm reacts to that component of the text. Wonderful. So I say this, I think the concluding remark for you is that the future of artificial intelligence applied to health is not AI versus the doctor. Just like it wasn't in the images to spreadsheet thing I showed you, the spreadsheet transcription. It's actually humans and machines working together. And that's because inevitably everybody here in this room, you're all taking in an insane amount of data actually relative to what most algorithms are. Algorithms tend to have these very narrowly defined sets of things that they look at to make their decisions, like you saw in both of the tasks. But you as a human being are looking up at this stage. There's an insane amount of data that your eyeball is collecting, and you know which subset of it to look at. Inevitably, if we're not going to put everything into a machine to consider, which we probably won't, at least for the near term, a collaboration between artificial intelligence and human intelligence is where we're really going to get the most bang for our buck. And I put this as the last slide because we published a paper about a month ago showing that this in the case of radiology, where even if you give a machine access to everything inside of an electronic medical record and try to explain the decisions of clinicians, even with access to all the structured data, there's still a component of the clinician's decision-making that it finds it difficult to predict. So with that, I'd like to thank you for your time and attention, and I'm happy to take any questions.
Mohammad, thank you very much indeed. We're going to open up the floor, actually, to ask any questions if they're forthcoming. If I can even talk. I can't even talk now, can I? Any questions for Mohammad in that fantastic presentation? Thank you for sharing just a snapshot of what you've been working on for a number of years. Anybody like to ask anything, please raise your hands. Gentleman just here at the front, and did I see 2 hands up there at the back? Yep, 2 over there. So we'll come to you, man in the red, and then the lady after. Thank you.
I was just curious, you're from U of M, you said also?
No.
University of Michigan?
No, I'm actually right now a researcher at MIT, but I'll be starting a faculty at Michigan State next year, probably.
Okay.
Okay.
But it was mentioned earlier about Asperger's.
Yes.
And I was just curious because, as I understood it, it was removed from the DSM-5. Is the community still using the term?
Well, I'm not a clinician, so I don't want to speak on behalf of the clinical community. What I can say is that in the conversation we've had with clinicians about the potential use case for the social coach I showed you at the end, they think that people who generally have problems with communication, people on the Asperger spectrum are one component of that, might find some utility there. But specific questions about what is defined as Asperger's and what is not, I'm not an expert to ask about.
Okay, we'll move on. Thank you. Gentleman over there in the red. Hi.
Hi. I want to ask you that how did you train your model with so little data?
Yes. Okay, so the way that you do it is, think about actually what a 10-person data set is like, right? These recordings can last for anywhere from 5 minutes to sometimes up to 20 minutes. So what you're interested in doing is saying, I'm going to take from each person different snapshots in order to take my data, which is right now short and wide, and try to create something that's slightly taller. Does that answer your question?
Yeah, partly. Yeah. Thank you.
Perhaps you can quiz him a little bit.
I'd be
Yeah,
happy
I
to
will
do that.
read the paper later. Thank you.
Okay, yeah, I think the paper probably have more detail in there, more meaty detail.
Yeah.
To the lady behind you, thank you.
I'm asking this question for my friend who's socially awkward. So, have you actually tried this with people who are socially awkward, or perhaps that you suspect have some kind of Asperger, like whatever we want to call it, kind of symptoms, and does it help?
So I can say, as somebody who considers myself to be a bit on the socially awkward side of things, I've tried it on myself, and the way that it ends up manifesting is when, let's say, I'm boring a person to death with the technical details of something I'm speaking about, it gives me a little buzz. So that's the way it manifests, right? If the person starts like looking away or yawning or whatever, then it'll give you a little buzz.
So that's very different than what you showed, though, because what you showed was more mood, and what you're talking about is more engagement.
Yes. Well, I think that the two, for the purposes of the initial use case we're looking at, are linked, right? So if the person is reacting to you in a positive way, the happy side of that spectrum, because the classifier actually looked at three things. It was trying to figure out, are you happy, are you neutral, are you sad? And so the immediate use case for that we're testing is, can I at least figure out when they're not happy, or they're happy? That's the idea. Just happy or not happy. The more happy the person it tends to be in the conversation as you're speaking with them, you'll get one kind of buzz. If they're not, you're going to get a double buzz or something like this, so that you discreetly know kind of some very ballpark, rough feedback on how well you're doing in the conversation.
So engagement is happiness. But you can't talk about something that's sad with this person. And so in other words, if you're having a conversation about your emotional state and you're talking about a sad story and they're sad, that means they're engaged in the conversation.
No, well said. That's precisely the reason why we wanted to figure out what sadness was, because we want to exclude that very thing you brought up. See, because it's about happy or not happy, but then you also have to condition on your ability to detect the sadness. Does that make sense?
We'll have to leave it. We'll have to leave it there. But it's fascinating to talk to you. That gut feeling that you're talking about, I don't think you can override that, though, can you? Really?
Well, at least not with what we currently have. Maybe one day.
Maybe one day. Who knows? Mohammad, thank you so much
my
for being
pleasure.
with us. Thank you so much.
Thank you very much.
Mohammad Ghassemi there.